Hey guys, this is Brent with Lykins Motorsports, and I have with me Jay Brown. I know that we've been discussing having him on the channel to discuss some new cylinder heads. Jay is the operator of the fepower.net website forum, which I'm on there quite often, along with a lot of other FE guys and FE engine builders. He is also the owner of FE Power LLC, and he produces quite a few products for the Ford FE engine. And I think that I have, over the course of several years, tried all of them. Very high quality parts, and that's why I'm looking forward to trying out these new cylinder heads. And I have a couple of builds that I'll be starting pretty soon, and I thought it would be an advantage to everybody for Jay to hop on and explain where he came from in the industry and all the testing that he's done, and to go over these new cylinder heads. So I know that I promised, well, I didn't promise, but I said that I would try to get this video out at the beginning of the week. Jay and I actually did this once already. We had 50 minutes of really good dialogue and discussion. And then when I went to edit the video, I found that I had zero audio whatsoever. So I felt like a complete heel for wasting Jay's time. But we're going to give it another shot. And before we get into the video, I would suggest you get a nice cup of coffee to drink while you listen to Jay. And before we start, I am going to pause the video right here and make sure that we do have audio and that everything is kosher. So it'll take me a few minutes here. You guys won't see any of that, so just stay tuned.
Okay. Well, Brent, thanks for having me on. I appreciate that. You wanted to know a little bit about my background, and so I'll tell you about that. I've been running FE engines since 1978. In 1978, when I was 19, I bought a 68 Shelby Mustang with a 428 Cobra jet in it. And I had previously been driving a 67 Mustang with a 289. And of course, as soon as I got into that Shelby and felt the power of the 428 Cobra jet, I kind of gave up on small blocks at that point. So I've been running FEs ever since. Along the way, I got an engineering degree, and I worked in engineering for 26 years, primarily focusing on product design and development. So I actually got started with FE Power back in 2010. And the first thing I did is I wrote a book. I had purchased a dyno back in 2005, and I started doing dyno tests of different intake manifolds. And the results were real surprising to a lot of people on the internet. And so I decided, well, I was just going to go forward and try to do a real comprehensive book about how the different manifolds work on in FE engines. And so I did that over the course of 2006 to 2010 and published my book. And this is a copy of my book right here. This is called The Great FE Intake Comparo. And basically it covers 6 different dyno engines that I built, ranging from 375 to 675 horsepower, and testing something like 40 FE intake manifolds, some of them ported or port matched. And so it's a really good book for somebody who's interested in looking at what manifold is going to work best on their particular combination. They can target a horsepower, they can look in the book and figure out which manifold works the best and all that. And what I found really interesting when I was doing it, besides all the regular data, was that there was a manifold combination that was made by a company called Pro Stock Engineering back in the late 1970s and early 1980s that was basically an adapter that you would put on an FE engine, and then you could throw a 351 Cleveland intake onto that. And that was real appealing to me, because there's a lot more good 351 Cleveland intakes out there than there are good FE intakes. So at that point, I got into designing an intake adapter similar to the one that Pro Stock Engineering had, but able to use modern CNC technology. And I worked with a local pattern shop to create foundry patterns. I worked with a local foundry to get castings, and I put a 4-axis CNC machine in my shop, and I started manufacturing these things. And that's kind of how I got going, manufacturing parts. I really had a lot of fun with that. It seemed like it was right up my alley, similar to what I was doing at my regular job in terms of design and development. So those have been pretty successful over the years. A lot of people, yourself included, have used them. A lot of people like them because you can put a 351 Cleveland tunnel ram on an FE, and there just isn't any other good way to get a tunnel ram on an FE. If you find a dedicated tunnel ram for an FE, they're few and far between. Mm-hmm. So got going on that, and then I started picking up some other products. I did a timing cover with a removable front plate. I did valve covers that look like pent roof cast iron or cast aluminum valve covers. I do these billet things called water pump adapters to adapt a 55 gallon per minute water pump to the FE engine, and so a few other products as well. And when I left my regular job in 2017, what I really wanted to pursue was cylinder heads, and I'd been kind of disappointed in the wedge cylinder head availability for FE engines, and so I wanted to do something a little bit better than that. I started my cylinder head development right away. Got a lot of help from people that knew a lot more about it than I did. One guy in particular designs aftermarket cylinder heads for a very well-known aftermarket cylinder head company, and I can't tell you who he is, but he was very helpful in getting me straightened out and down the right path there. And so I got these things developed and showed them at PRI and ran some tests on them on the dyno, and was real happy with them. Kind of went to production with them at the beginning of 2021, and then right about that time COVID hit, and the aluminum foundry business just went in the tank. And so it's been quite a long haul since then, getting castings and trying to get these things out to the market and to my customers. But things like they're turning around a little bit now. I recently got a batch of 10 heads. I'm expecting another 10 or 12 from the foundry here in January. So a little luck where that part is behind us, and I'll start being able to have these things put out and in the basically on the shelf for people to buy. Good. Again, going back to the reason that I did this, I was always a high horsepower guy, always looking to make as much power as I possibly could. And in order to get a really top shelf set of wedge cylinder heads, I was finding I was having to pay $6,000, $7,000, $8,000 for a set of heads. And that just seemed like an awful lot of money to me. It seemed like for what you got, you were paying an awful lot for it. So when I started doing my own, I decided to learn as much about it as I could, and there were several things that I learned that were pretty important. I think the most important thing that I learned was, well, let me just say, the three most important things I learned were that the most important things on any performance cylinder head are the intake port and the intake port and the intake port. I spent a lot of time on the intake port. Of course, the chamber is important, mostly because it's got to work with the intake port to get the air into the cylinder. The exhaust port is important, but not as important as the intake port, because of course you've got residual pressure in the cylinder that helps the exhaust get out when the valve opens. So all you've got on the intake port is atmospheric pressure, and cylinder filling is what makes horsepower. So that was a big thing, a big focus. And I probably have close to 200 hours in the development of my intake port on my cylinder. Another thing I learned was modern thinking is that you increase the size of the intake valve and then decrease the size of the exhaust valve. So when you decrease the size of the exhaust valve, you can decrease the exhaust flow a little bit and you'll lose a little power, but increasing the size of the intake valve and making it match, making it work with the port picks up a lot more than you lose. So if you look at any modern cylinder head that's been designed in the last 15 years as a performance cylinder head, it's typically going to have a much larger intake valve than the exhaust valve. A real typical number might be a 219 intake or 225 intake and a 1/600 exhaust. Those are real common numbers. And on my heads, I went to a 2.300 intake and a 1.675 exhaust. So that was another thing that was important. The last thing I thought was important, and I had known this for quite some time, is that you want to keep the intake port as small as you possibly can. And the reason is that when you keep it small, you have good port velocity. Port velocity is really important. If you have a really, really big hogged out port, it's a slow, sluggish port. The flow starts slow and it doesn't have velocity at the end of the stroke. So for example, when the piston is coming up and the intake valve is closing and you still want to be pushing some air fuel into that cylinder, if you have a lot of velocity behind that air fuel charge, you'll get more in there. So you'll get much more cylinder filling out. So those are the things I think is the key things for me anyway. We're really focusing on the intake port, biasing the intake valve so that it's bigger than the exhaust valve, substantially bigger than what's typically found, and trying to keep the port cross section small. So now I'm going to talk a little bit about what we actually did, what the kind of the process is here. So I'm going to zoom in here, see if this works. Hey, look at that. So what we're looking at here is just a poppet intake valve. And what everybody has to understand about this is the ideal flow on a poppet intake valve is straight down the valve stem so that the flow goes around all sides of the valve. That's when you get the most flow. That's when you get the most efficient flow. Okay. And now, bearing that in mind, we're going to look at an FE port. This is a rubber mold casting from an Edelbrock cylinder head. And what you can see here is that you've got a fairly sharp angle here where the flow has to go around this corner and down to the valve. And the flow has a hard time doing that. Now, the flow wants to stay connected to that wall, but when you start getting a lot more velocity, it can't get connected to that wall, and it'll tend to blow across the valve, and you can fill more air that way, but it's not as efficient and you won't feel as much air as if you were getting the thing all the way around. So that's one drawback of this design. And let's not forget that the FE engine was originally designed in the mid-1950s. I mean, it didn't show up in cars until 1958. And so a lot of development of this stuff has happened since then. And that's a pretty important thing to think about. Another thing that I didn't like about the stock FE intake port was that it's got a hook in it. So if you look at that, you know, the air, instead of going straight in, it's kind of coming in at an angle. And when it comes in like that, it aims that flow kind of against the cylinder wall. And you'd like to have it aimed right into the middle of the chamber so that you give it as much room as possible for the flow to be there as you can. But this port doesn't do that. It aims it more there. So that hurts you from a flow perspective. So we're going to look at that port there for a second. Now we're going to look at my port. This is a 3D printed version of my port. And one of the things I want to point out here is that the cross-sectional area of these ports is nearly the same. My port turns out to be about 4% larger in cross-sectional area. So you still have a pretty small cross-sectional area on this, but this port will flow 60% more air than a stock port. And the reason is, number one, you've got a very, very smooth turn here. So, I mean, this is kind of like driving a race car, right? I mean, when you drove a race car into a really sharp corner, you got to slow down. When you got a gradual corner, you can keep the speed up. So the velocity that you can maintain on this port is much, much greater than the velocity you can maintain on the factory style port. In addition, you'll notice this flat area down here, a straight area. So that's where we're trying to get the air to flow straight down to the back side of the valve so that when it hits the valve opening, it goes around all sides of the valves. And like I said, this particular intake port flows a little over 400 CFM, whereas a typical stock type medium riser or Edelbrock port flows around 260. So about 60% more flow, same cross-sectional area. You can really pack a lot of air fuel mix into this port. So this port really I spent a lot of time on this, and it really seems to work quite well. Talk about the exhaust ports for a second. Here's an exhaust port casting, again from an Edelbrock head, and you know you can just tell it doesn't look that great. You know, I mean, it's and the exhaust port again isn't as important, but you know, you want to get it to be as good as you possibly can, right? When I decided to do my first exhaust port, I decided to completely change this and raise the exhaust port and have it come out parallel with the ground. So that's what this thing is. This is one of my exhaust port 3D prints. And you can tell just by looking at this how much more air this is going to flow, and how much more efficient this is going to be. So I got going on that, and I started. I built some test heads using this, and put some information out on the website about that. And then I started having people say, "Well, are these going to work with a shock tower car?" And no, they will not. There's no chance they're going to work with a shock tower car. And beyond that, you got to build your own headers for these. So I bowed to the demands of the market and did an exhaust port that has the port in the same position, but I did still make some changes to it. So this is my standard SE, what I call an SE, stock exhaust port. And you can see the big difference here is that this is kind of like a header tube up here. I'm using more area there than the stock ports did, just so that I can make the flows as good as possible. And as it turns out, this port right here, the stock exhaust port, flows the same as a stock FE medium riser intake port. So it's a pretty good flowing port. And then this one is so now we've talked a little bit about the actual design and physics behind this whole thing. Let's look at some of the cylinder heads themselves. So this is one of my cylinder heads here, and this is actually next to it is an Edelbrock head. And the first thing I think you want to take notice of is how high the port is raised, and you saw that from the models that I showed. But this port is about the same size as a medium riser port, and it's raised 1.5 inches over the medium riser location. So that's a really good thing for flow. And the other thing, of course, is that it's a straight in port compared to a hooked port. So if we rotate this a little bit, you can see that if I stick a pencil through here, that's a straight shot into a nice fat part of the chamber, so it's really good for flow. If you try to do that with a standard FE port, you end up going in at an angle like that, and again, you're pushing against the cylinder wall there. So those are the primary differences. And by the way, Ford knew about this back in the day. You know, they did some racing engines. You're familiar with the tunnel port, and I've got a tunnel port head here that we can look at, which is much heavier than a aluminum port. But if you look at that, the ports in my heads are in about the same location as the ports in a tunnel port head. So you know, Ford had that in mind when they did the tunnel port design, and I think that was a good thing. Now one of the things that Ford did with the tunnel port design that I didn't like is they put a pushrod tube through the middle of the intake and ran the pushrod through that, and I wanted to avoid that. So we'll go into how I avoided that in a minute here. But I'll turn this around for just a moment, and you can see the raised exhaust port that is done with my heads, my RE heads, my raised exhaust heads. And again, this port comes straight out parallel to the ground, and it's pretty easy to make headers for it. But like I said, they won't fit in the shock tower car. So we'll pull another one up here in a minute that has the stock exhaust type. What I want to talk about now, though, is all this greatness of these intake ports and how much flow and it doesn't come for free, right? There's downsides to it. So what are the downsides? Well, the first downside is no FE intake manifold is going to fit on these. You know, the valve cover rail is different. The ports are in the wrong location. You know, blah blah blah. So that's an issue. And the second issue is no FE rocker arm system is going to fit either, because the whole thing is designed differently. So what I had to do when I started doing this project is I had to commit to doing pretty much complete top end of the engine, heads, the intake manifold, and a rocker arm system. So that's kind of what is available from FE Power on these is a whole package. So give me just a minute here, and I'm going to pull up one of my other cylinder heads that has some of the rocker arm system on it, and we'll look at that. Okay. So this is one of my stock exhaust heads. You can see the exhaust bolt pattern is the same as a 428 Cobra Jet pattern, and the ports are in exactly the same position as any other FE performance head. But what I want to talk about here is the rocker arm system. So I'm going to lay this down, and I guess I'll flip it around. so we can kind of see what's going on there. Maybe if I zoom in a little bit, we can see it a little bit better.
There you go.
So, so the first thing to notice is this thing right here, this bar that goes all the way along here. There's another one right here. You get an idea of what that looks like. This bolts onto the cylinder heads and holds the individual rocker pairs. And it bolts on in two different ways. It's got 8 bolts that actually go directly into the head itself, into the aluminum of the head itself. But then there are also 5 bolts, like this one on the end here, that go into a special nut that goes on the head studs. So here's one of these special nuts right here. And this is just basically a 1/2-inch head stud nut on one side. And then in this hex, there's a 3/8/16 thread that goes down into the counterbore holes in the top of the head, and this bolts down in there. And as it turns out, the angle between the bolts that go into here and the bolts that go into the head are a little bit different. That makes it really, really stable. Instead of having just one axis of control there, you've got 2. So that's a real nice, rigid, solid space for the rocker assemblies. And here's one of the rocker assemblies here. And what you need to notice about this, let's see, can we see that here?
Yep.
Maybe I got my pan a little bit differently. Here we go. So that's one of the rocker assemblies. And if you look at it closely, you can see that one of them has a huge offset. That's the intake rocker. And the reason for that is that you need to have the intake push rod coming up at an angle to miss the port. Otherwise, you're stuck with that whole tunnel port deal where you've got to have a tube through the middle of the intake. So I'm going to stick one of these things on here. In fact, I might have to use the other one. Yeah. So this goes on here just like that. They're individual rockers. And as you can see, they I'm going to move this a little bit. If you look at the intake rocker, you can see it's got a little bit of an angle to it. Again, I'm going to try to zoom in here. Get this fancy thing to work. So this intake rocker has got an angle to it, and the push rod comes up like this and slides by the side of the port in the intake manifold. So my pencil is too long to show this, but regardless, that's how the whole rocker arm system is. So they're individual rockers. I started off with aluminum rockers with these, and the problem that I ran into with the aluminum rockers was they just couldn't take the intake side couldn't take the torque between, or the torsional force between the push rod and the spring. When I first got going on these, I wanted to really wring them out and make sure that everything worked as in serious with some serious spring pressures. So I had 375 on the seat and 1,050 over the nose on the first cam that I started running these things at. And what I found was while the exhaust rockers seemed to hang in there pretty well, the intake rockers would start failing at about 60 or 70,000 cycles. And, they got to go millions of cycles, right? So that really wasn't a very good solution. So I ended up going to these rocker arms, which are an investment cast chrome moly steel rocker. And I have beaten the tar out of these things, and they just seem to live. So everything, I'm real confident with these. They work out very well. It's nice to be able to just pull off one pair at a time if you feel like it. It's a very nice setup. So I'm very happy with these, and these I've taken them to the dyno to 7,800 on the dyno without any trouble at all. I'm sure they'd go to 8,000 RPM if anybody wanted to go there. That's basically what the rocker system does. Now, one other thing about the rocker system, everybody's concerned about rocker arm geometry. This guy right here can be set on these little spacers.
Nice.
And so you can raise this thing to get your rocker geometry right where you want it. And as it sits right now, you can bolt it straight on like this one is, and that should be good to give you good rocker geometry in a 900 lift cam. If you're going to go less than 900 lift, then you should end up with running some of these shims. And I provide an assortment of these shims with the kits that include the rocker assembly and the cylinder head. So that's pretty much everything there. The last part is the intake system. And so I'll get to that here in just a second. Let me move some stuff around and we'll show you that. Okay, so now we're talking about the induction system for the cylinder head package. And it starts with this intake adapter here. And this is real similar to the ones that I've been making for years for a 351 Cleveland. But of course, it won't fit because the ports are in a different location and all that. What I really like about this is it's got this plate in the middle here, which you can unbolt and you can get into the valley of the engine if you need to do any work in there or whatever, and not have to worry about taking off the valve covers and taking off the rocker system and pulling the distributor, breaking the water jacket, and all the other rigmarole you got to go through with a regular FE just to get the intake off. With this one, you just take the intake off the bolts and you take that cover off and you're in good shape. So I started off doing 3 different intake manifolds for this, and I've got some 3D printed ones here that I'm going to throw on here to show you. This was the first one we did. This is a single 4 Dominator style intake manifold. I did this actually in aluminum at first and ran it on the dyno. And then I sent it down to Joe Crane, my friend Joe Crane in Texas. And Joe ported it and got back and picked up 15 or 16 horsepower with it. And so then I changed the design to incorporate what Joe did into the actual design. And this is just a plastic version of it. I haven't had the new version with Joe's modifications cast yet. Another thing about this is that this is plastic. I print this on the 3D printer. This is just a wonderful way to do product development. I mean, there's a couple $100 worth of plastic here and maybe a week on my printer, and then I can put this thing on the dyno and I can test it. But before I put it on the dyno, I have to coat it with some like an epoxy paint or something. I found that out the hard way. Despite the fact that this plastic looks like it's airtight, it's not. And the first time I ran one of these things on the dyno in plastic just like this, I had a backfire and it blew into smithereens. It was quite spectacular, actually. My friend Royce and my friend Kevin were here, and there's a big fireball, and the carbs are hanging over the valve cover on the left side. It was crazy, but we learned that lesson, and now I paint them all with an epoxy garage floor paint. And then, as long as we don't backfire when you run it, you can actually get good data on there. And on a couple of the manifolds that I've done 2 or 3 different iterations of them and picked up power by changing some of the designs a little bit. So from an R&D perspective, it's very, very valuable and not that expensive. That's one of the ones that I did. Another one. This one is a plastic model of actually the one that made the most horsepower. This guy here made like 894 horsepower on the dyno with a couple of Dominator carbs. And this one also got Joe Crane's treatment, ported treatment, and allowed me to make some changes to the manifold to improve its performance a little bit too. And the last one I did was an individual runner manifold, and I'm going to horse that thing over here right now. It's heavy, but it's really cool. Let me see if I can get this for you.
It looks
so this
heavy.
one is EFI only. And the rationale for this one is I wanted a manifold that would make a lot of torque for a street car, but would fit under the hood. So this one is actually quite a bit lower than the other manifold, but it will fit under the flat hood of a Mustang or a Torino or whatever. It's complicated. You've got this complicated linkage system, and you've got fuel rails tucked underneath and vacuum line tucked underneath and all that sort of thing. But it really, really works well. We'll show some dyno results on that in a little while. So these were the 3 I started with. And then I got to get some feedback from my customers. I use my website a lot for that. I go onto the forum, I post some information, and I get a lot of valuable feedback from some of the people on there, what they want to see and so forth. And one of the things that a lot of people wanted to see was a lower 4-barrel intake manifold. So again, bear with me. I'm going to move this and throw a couple other ones on there. So this one here is a lower 4-barrel intake manifold. Now, it's still going to be pretty high compared to a stock type intake, but it has the factory slant to the carb pad, and it's got the carb pad in the same position as a 428 Cobra Jet manifold. It's about 2, maybe 2.5 inches higher than a 428 Cobra Jet manifold. But if someone was to use an EFI system, you know, with a fairly small throttle body, I think it would fit under the hood of a shaker car and work with a shaker. So that's kind of cool. That's interesting. And this one, it made more power than I expected. It wasn't quite as good as that big 4-barrel intake, but it still did pretty well. And then a lot of guys really like the tunnel wedge manifolds. So I did one of those too. And this is one of the ones where I did multiple versions of it to try to make as much power as I could. Just to give you an example, when I started with this one, the first one I designed on this engine that I was testing it on, it made like 825 or 827 horsepower. Third iteration, it made 875. Wow. So moving, you know, the runners around a little bit and changing some of the cross sections of the runners and all that, it really made a big difference on this manifold. So that's a pretty good one. The last one I did is one that I should have probably done right from the start. A tunnel ram, because you know FEs are kind of 60s and 70s engines for a lot of guys, and having a tunnel ram intake is you know, it's a real throwback, right? And this manifold didn't make as much power as that other 8V manifold that I have, but it made gobs of torque, huge amounts of torque. So so this was a real good one. I want to do one other thing here before we get too much farther, and that is I want to show you some flow figures for the cylinder heads. So see if I can pick that up here. Right there. So now this is flow numbers for both the RE head and the SE head, and the flow was done on a Superflow SF600 flow bench with 28 inches of water, which is pretty standard. This is without any porting, but with a 5-angle valve job, a good 5-angle valve job, and a blend of the valve job into the bowl. And what you see is the intake flow on these both heads is the same because the intake port is the same. And you know, 700 lift, I got 403 flow. 800 lift, I got 416. You know, you're at a 1/2 inch lift, you're at the 342 flow number. That's a pretty big flow number for a 1/2 inch of lift. For sure. On the exhaust side, you can see that the RE head flows like around 277 at 800. The SE head flows 252. So the RE head's about 10% better on exhaust flow. But either one of them will work quite well with the intake port, you know, assuming you have the cam set up right. And in fact, Brent, you helped me a lot with that. You got me a cam that had a little bit more exhaust duration, and that crutched some of these flow numbers a little bit. I think that we got on the exhaust and made a lot more power that way. So I appreciate that. I want to do one other, show you one other thing as well. So again, my friend Joe Crane has been really helpful in getting this project up and running. And I sent Joe a set of the SE cylinder heads, and he ported them for me. And here's one of his heads. So now Joe basically tried to do what is essentially a max effort porting job on this. And I don't have the numbers in front of me that he got, but they were around 440 CFM. And his comment to me was, it really needs a bigger intake valve. So I went out and I bought a set of 2.35 inch intake valves and and there's room for them in there. And I had those stuck in there. And this head with those intake valves flowed 459 at 800. That's a big number. So this is a 1,000 horsepower cylinder head here. There's no doubt about that. I mean, anybody with a decent bracket motor can make $1,000 or 1,000 horsepower with a head like this. So thanks to Joe for that. He did a great job for me on that. And I'm looking forward to trying these. I haven't gotten a chance to do that yet. We'll get there with it. So now maybe we should talk a little bit about some dyno numbers. So the first thing I want to say about dyno numbers is I own my own dyno. I'm an engineer. I keep it calibrated and accurate. And that is not the case with all dynos.
For
So
sure.
the numbers I'm going to give you, the numbers I'm going to give you are real life accurate dyno numbers. They're not the ones from a place that will run a 5 or 10% high just to keep the customer happy. I don't have any dyno customers to keep happy. I'm just interested in keeping myself happy. So let's take a look at some of those. So first, let's look at a comparison between the RE heads and the SE heads, and that's this right here. Now the RE head intake or the RE head information is up on the top here, and with that 8V intake, the RE heads made 894 horsepower at 6,900 RPM, which is not a lot of RPM, by the way, for that kind of power level.
No,
The SE heads were down. Yeah, the SE heads were down about 25 horsepower from that. So the exhaust port hurt us to the tune of about 25 horsepower, but still 870 horsepower at 6,700 is nothing to sneeze at. And they both made about the same torque, about 730 foot-pounds of torque. We go to the 4-barrel intake, that tall 4-barrel intake, and we drop down to 870 horsepower with the RE heads at 856 for the SE. So there's only about a 15 horsepower difference there. And again, the torque is very similar, 719 and 723. So the dyno chart that's shown here is the one with the 894 horsepower number. And what I like about this chart is that you get up to the peak horsepower at 6,900, and then the motor just hangs there, making 890 plus horsepower all the way to 7,500 RPM. And going back to what we talked about to begin with, keeping the port cross-sectional area small, I think here is where we're seeing the port cross-sectional area start to limit the power. And you see that sometimes. I've seen it before at camera motors where, you know, just because the port isn't quite big enough, it'll just hang there at that same power level for an extended period of time. Pretty sure that's what's going on. Mm-hmm. This particular setup made 735 foot-pounds of torque right in here. I think if we put a bigger port in there and a little bit healthier cam, ran to 7,500 to 8,000, I'm pretty sure you can make 1,000 horsepower with these heads, just the way they are. So then, let's look at how these different intake manifolds did. Let's see if I can find the 4-barrel manifolds. Let's see, here we go. So this black line up at the top here is that first red 4-barrel intake that I showed a little earlier, and this little lip up here is just kind of it wouldn't hang there. It would come back down and stay in that area like that. But that shorter one is this red line, and it's not really that far off. I mean, it's over 800 horsepower from 6,000 RPM on up, so it's still pretty good. And then, just for fun, at the higher RPM levels, I added a 1-inch spacer onto that shorter manifold, and that picked it up this much. So it really wanted more plenum than that manifold has got. Anyway, 4-barrel intake. This is all pretty good stuff. These things are all running right around 700, 710, 720 foot-pounds of torque in the mid-range here. So it's a nice it's a very nice setup for the 4-barrel. Now, if we go to the two 8V manifolds, let me see if I can find those here. Here we go. So that first one that we showed, here's again that flat spot up here going up to 7,500. The blue lines here are the tunnel wedge. And amazingly to me, it made a bunch more torque at the bottom end than that larger manifold did. Oh, maybe it's not amazing. It's just remarkable that the difference is that much. I mean, we're talking 60 horsepower from here to here. You know, that's a big amount, around 4,500 RPM. And then it fell off a little bit up at the top compared to the other one, but not that much. You know, this is still an 875 horsepower intake. So this data was also very encouraging with that particular manifold. And then the one I really like is the one with the tunnel ram and the individual runner intakes. So and the individual runner intakes are really interesting. They always go up and down like a roller coaster. Here's the torque curve for that individual runner intake. And man, I'll tell you, on the dyno, when this thing is heading towards 3,800 RPM, boy, it just sounds like it's ready to fly off the dyno. And then it dips down and does the same thing again. And this one actually made the most peak torque of any of the manifolds. It peaked at 765 foot-pounds, which is 1.5 foot-pounds per cubic inch. Maybe a word about the dyno mule. This is a 511-inch FE, 4.31 bore, 4.375 stroke, 800 lift cam, and the heads that were on there are the RE, the raised exhaust heads for all these dyno charts. And they're unported. You know, they have the valve job, they have the bowl cleanup under the valve, and that's it. The rest of the port is as cast. So this isn't anything special being done to these things. This is all pretty much the way people are going to run them before they do any porting. Anyway, the red line is the torque or the horsepower. Excuse me. The blue line is the horsepower for the individual runner intake manifold, and it kind of hangs around up here, right around 800 horsepower, and then it jumps up at 7,000, and it might stay. It might go up a little bit more than that, probably not too much. The tunnel ram is the black line for horsepower and the red line for torque, and the tunnel ram again made 763 foot-pounds of torque. So that's again 1.5 foot-pounds per cubic inch. That's a huge number. I've never had an FE that makes a number that good in terms of the peak torque. So the thing with the tunnel ram is that it gets up here to about 6,400 RPM and it's done. It just starts to fall off after that. And that's real common with tunnel rams because the runners are really long. Mm-hmm. So the shorter runners on that other 8V intake are what kept it going up towards 900 horsepower and kept it hanging in there at the top. So that's kind of the data that I have so far on these. The dyno mule that I had this on, it's 13-to-1. It has a vacuum pump. You know, it's a really typical bracket race engine, and it'd be easy for somebody to duplicate. Nothing special about that at all. When I got done, it had been on my dyno for over a year and a half and had close to 250 dyno poles on it, and it was, man, I just beat the tar out of that thing. It was, and it just hung in there. It was really a good motor, and I'm going to go through and freshen it up again here. Maybe put Joe's heads on it and shoot for 1,000 horsepower next time. We'll see how that works out. But regardless, that's kind of the data on that. So back to the intake manifolds for a second. The original plan was just to do 3 intakes. Now I'm going to do at least 5. I'm not 100% sure I'm going to do the tunnel ram, but the thing that saves me on this is I can 3D print the sand, believe it or not, for the foundry. And so I don't have to spend a whole lot on tooling to tool 5 or 6 manifolds as compared to 3 manifolds. So that's a plus. And I think the only other thing I want to talk about is the pricing of this stuff. So I haven't figured out what the new pricing is because everything has gone up over the last couple of years. But the guys who got in early are paying $6,000 for the cylinder heads, the intake adapter, and the complete competition rocker arm system. So that's less than what you'd end up paying for a really high-end set of hand ported or CNC ported cylinder heads, at least the ones that make the kind of power that this thing will make. So that was, again, the rationale for me going forward with this, is to be able to put together a package that somebody could bolt on, get them to 900 or 1,000 horsepower without breaking them. So that was the rationale behind this, and I think I've hit that. And it's just a matter of being able to get the castings done now for the manifolds, and I'll have the whole package ready to go.
Yeah, I mean a good set of rocker arms. If you look at something like a T&D paired rocker for the FE, I mean the rocker
Yep.
arms themselves are up close to $2,000. So
Yep.
you lumping that in there is awesome.
Yeah. And of course I had to do it. I had no choice.
Yeah.
But since I'm doing it all myself, it's I mean, I could probably get somebody like T&D or Jessel to do my rocker arms, but then I'd be throwing $3,000 or $4,000 probably on top of this, because it's a low volume kind of a thing. This is
Right.
this is the problem with any FE stuff, is that it's low volume, and so getting somebody who wants to do high volume stuff interested is difficult to do. So, but we'll get there with it, and with a little luck, I'll make it to drag week with one of these engines here sometime in the next year or two, and really prove it out there.
Yeah, that'd be awesome. I like
Yeah.
the intake adapter. I ran one on Project Junkie Junk, the 352, and
Yep.
it was easy for me to do cam swaps. You pop the intake
Yep.
off, you pull the cover off, and you could literally just reach in there and pick the lifters up by the link bar and just push them up out of the way, and
Yep.
slide your cam out, put your cam in. I mean, it was great. So
Yep.
between your Dyno Mule and your projects that you have going on, I have two right now, as of right now, to go together. One is a all aluminum 496 using your cross. I guess you would call that a cross ram, yeah, EFI.
Right.
The heads that I have for that engine, as you know, were ported, and they do 430 CFM at 800 lift. So I was able to squeak out some nice cam specs to actually make a streetable solid roller
Yeah.
camshaft that doesn't require 1,000 pounds of spring load. So I'm aiming to take advantage of as much lift as I can, because you get up there and you make horsepower. So
Yep. Yep.
that engine will have a custom billet Bryant crankshaft, which we're waiting 24 weeks for that crankshaft. It has titanium valves. It'll be a dry sump engine. And then the other engine is, I believe, a 510 and cast iron block, and more of a bracket race type engine. So I will have a little bit more freedom to kind of squeak some more horsepower out with that engine. So I'm looking forward to doing
Yeah.
both of them. And
Yeah.
if you guys that are watching, you want to hit that subscribe button so that you don't miss out on any of this stuff. You'll have to be patient, as Jay can attest. This stuff takes a while to do. It takes a while to get parts, and to be an engine builder in post-COVID days, you have to have a lot of patience, because things just don't show up at your door the way
To be a manufacturer in post-COVID phase, you got to have a lot of patience too.
Oh my
I think
goodness.
I put an order in for 60 cylinder heads with my foundry in March of 2021, and through August I had gotten 10.
Oh,
It's just ridiculous, just
yeah.
ridiculous. Now they're finally starting to come out, so that's a good thing. But
It is a very good thing.
yeah. Yeah.
All right.
So,
Well, thank you very much, Mr. Jay Brown, for coming on the channel and showing us all the cool goodies. And
Thank you, Brent. It's good having a discussion with you about it.
yep, and I plan on later this week posting another video. I'll be assembling this set of heads here that I have. I'm using some Ferrea titanium valves and some Manley Next Tech valve springs and some other goodies. So I know Jay wasn't able to get stuff right up in front of the camera, but I will try to do that so you guys can get more of um, a detailed look. The heads are beautiful. Copper beryllium seats, right, Jay?
Yep, that's right.
Yeah, just high end parts. Five
That
sixteen
was a
stem.
special for this one customer, by the way. They don't all come with copper beryllium seats.
Okay. Yeah, I'm
This
glad you
customer
mentioned
had,
that.
yeah, he was going with titanium valves. I do have valves that I've done for the heads as well. I contracted with Ferrea for that. I have a hollow stem intake and a solid stem exhaust that works with the heads. They're a 5/16 stem valve, and so you've got to have you can't use you can't use regular ethylene stuff on these.
Yeah.
But the customer that wanted the copper seats, he wanted to run titanium valves, and that's why. So most of them come with regular seats.
Yeah, and the valve lengths are what, 6 350, right?
About that, yeah, I can't remember right offhand, but
Yeah.
they're long because the board is high,
Mm-hmm.
and they're 5/16 stem, and again 2 300 on the intake, 1.675 on the exhaust. So,
Yeah, even with that length, even with that long valve, the intake valve, the titanium intake valve, is well under 100 grams on this engine. So, good
yeah.
stuff. All right, guys. Thank you for watching, and I hope to have. Well, this won't pertain to you because by the time that you click on it, it'll already have been edited. But I plan on doing that hopefully this evening, and hopefully we'll have audio this time. Jay, I apologize for that, but thanks to everybody for watching, and I'll see you soon.